Okay, we have our first exam. Our exam 2 is on Wednesday, and I posted the review, which I believe was 24 questions, and then I posted the solutions to the review, and I was telling some of your classmates the review took me like 2.5 hours, I think, to do. Which means that you should put a lot of time into that review. It should take you a while. But your test on Wednesday will not be 24 questions long. I mean, there's just no way you'll have enough time for that. So what I try to do is give you like a good mixture. For example, on the first three problems all involve taking the derivative using the limit definition. And so on the test, you're probably not going to have 3 problems doing limit definition. You'll probably just have 1. And a lot of the problems are like that, where I give you, there's like 3 or 4 problems in here that are all power rule. And then I'll probably just do one problem where you have to show power rule. And then there's mixtures of quotient and chain and things like that. I'm not going to give you 10 problems like that, just 1 or 2. So don't be too afraid with the length of the exam, but there were some subtle things in the review that I didn't necessarily do exactly that type of problem in class. So I was hoping you would have some questions about that. But first, there's a homework question I want to address. Okay? So I've been asked about number 25 from section 2.6, which was 9x squared plus y squared equals 9. And you're asked to find y double prime. Is this okay, or do I need to turn the lights down? It's okay? All right, I'm going to shut the door, though. This is very similar, this problem, to the last problem on the review, I believe. So if we're trying to find the second derivative, what we'll do is we'll find the first derivative, and then after that, the second, right? So for this equation, I'm going to use implicit differentiation. So that means I'm going to do derivative of the left and right-hand side separately, applying the chain rule, remembering that the derivative of x is 1 and derivative of y will be y prime, or dy dx, whichever notation you prefer. So the derivative of 9x squared will be 18x. What happened? Everyone showed up today. I think, is that what happened? Is that why we're out of room? Everyone showed up today, the day before the test? Okay. 18x. And then plus, now the derivative of y squared. 2y times dy dx, or y prime. That's the big deal, right? That's the big thing that we need to understand going into the test, is the chain rule applied right here. And then the other side equals 0. Now, I have 2 options here. This is what I didn't really get too deep into last class. And that's, I can just do the derivative again to get the second derivative, or I can solve this for y prime and then take the derivative on both sides. Either way, it turns out to be easier, though, if you solve it for y prime. I'd like to show you both ways. So let me just take the derivative right now. Again, implicit. What is the derivative of 18x? 18. Now, this is the part that gets tricky. Plus the derivative of 2y times product times y prime. So I have to apply the product rule right down the middle here. What is the derivative of 2y? 2y prime times, so I'm doing product rule, derivative of the first one, that's this, times the second, so times y prime again, right? Plus, now the derivative of the second one, what's the derivative of y prime? Y double prime. So there's your second derivative. Then times the first one, 2y. So what's in red here, it's kind of hard to see it's red, but is your product rule on that piece right there. We're done on the left side, equals derivative of 0, which is 0. And now you have to solve for y double prime. So I need to get this by itself. So I have 1, 2, 3 terms. I can move this 18 to the other side, the 2 y prime times y prime to the other side, which makes them both negative. Watch what I do here. Does everybody agree with this? It's minus, yeah, thank you. It's minus 2y. Now, y prime times y prime is y prime squared, not y double prime, right? And then finally, I'll divide both sides by 2y. All right. Now, that's not the answer in the back of the book, okay? Because what they did is they came in here and they replaced y prime with whatever y prime was, which means you would have had to have gone back up to this equation right here and solve for y prime. So I'm going to do that. I'm going to take this. If I solve that for y prime, I move the 18x to the other side. So 2y, y prime equals negative 18x. And then divide both sides by 2y. You get negative 9x over y. Do you all agree? Divide the negative 18 by 2, you get negative 9. Divide x by y, you get x over y. So that's what y prime is. Now I can take that and plug that in right here, right? And this is where it's going to become an algebraic mess. So I have y double prime equals, can I reduce everything by a factor of 2 here? Is that okay? All right, so I'm going to have negative 9 minus, now my y prime, which we said was negative 9x over y squared over just y. That's still not what the back of the book has, right? So let's square this right here. Y double prime equals negative 9. When you square 9, it's 81. Negative 9 is 81, x squared over y squared. So minus 81 x squared over y squared over y. Then what they probably did is get a common denominator between these two, right here. So they introduced y squared on top and bottom of this. Let's see what that would become. Negative 9y squared minus 81x squared over the new common denominator, which is y squared. Do you all follow that? That's just these two fractions right here put together. And then all of that over y. But then you can take that y that's on the bottom, look at it as a y over 1, and flip it and reciprocate it like this, and that just really makes that bottom a y cubed. Right? Right? So I would be at negative 9y squared minus 81x squared all over y cubed. That's not what the back of the book has? They probably split it up into 2. Oh, they factored 9 out? Oh, is that all? What did the back of the book have?
It was negative 81 over y cubed.
Negative 81 over y cubed?
Yeah.
Okay. So let's see if we can get to the back of the book. I'm going to highlight what they have up here. All right, let's see if we can get to that. Right now, it looks like we have a mess, don't we? Okay, so let's check this out. I think I see it. If you factor out a negative 9 out of the top, you'd be left with y squared plus 9x squared. Do you agree with that? If I factor negative 9 out of the top? Yes? All over what? Y cubed. And check this out. What is x squared, 9x squared plus y squared? Go back up to the very beginning of the problem. What's 9x squared plus y squared? It's 9. Right? If this equation is true the entire time, right? Then at the end, if we ever see that, we can turn it into a 9. That's what they did. So this becomes negative 9 times 9 over y squared, or cubed, which is that. Okay, so on your test, what I'm looking for is at least you're getting the implicit differentiation correct, right? At least that derivative. As far as simplifying and stuff, if you run into issues or you didn't see this, you know, I'm not going to penalize you. This is not incorrect, all right? It's not incorrect. You just haven't recognized that that's 9. Questions? What's that? Just, no? Okay. Now, if I were doing, remember I said I would show you both ways? I did implicit once, implicit twice, and then I had to simplify, and it was kind of a mess. If instead I would have gone straight from here to here and solved for y prime, I could have done my derivative here instead. Do y'all want to see that? I mean, it's a little cleaner. The derivative of this, what's the derivative of the left side of this? What's the derivative of the left side? Y double prime. On the right side, what rule do I use over here? Quotient rule, which is the derivative of top times the bottom minus derivative of the bottom times the top all over the bottom squared, right? So this would be derivative of the top, which is negative 9 times the bottom minus derivative of the bottom, excuse me, y prime times the top, negative 9x, right? All over y squared, which is pretty much, I'm trying to see, it's almost this, right? Yeah, you'd still have to come in here and do what? Replace this y prime with what? With this right here. And then get a common denominator and put together just the way we did a second ago. So it would work, but the derivative was kind of clean that way. It's quotient rule. Either way is going to take you to the same place. And when I'm grading these, I will pay attention to which way you went. And if you go a certain way, then I'll follow that work. As long as it's, you know, legitimate, then there's no issues. We got a full house today. Where's everyone been? Missing classes? All right. Miss class at your own risk. Right? How to get to what? Where's that? Right here? Is that what you're talking about? Oh, like the actual quotient rule? Yeah. Yeah, I didn't show the quotient rule. I did the quotient rule mentally. So it's the derivative of the top, which is negative 9, times the bottom, y, minus derivative of the bottom, which is y prime, times the top, which is negative 9x. What was the other question? Right. Was it a question on the review? Whichever one you want. I think when I did h to 0 the whole time.
Yeah, you said there was a certain limit definition you gave us.
So you could use either one. Well, but the limit x approaches a, you can't use that one if you're trying to find f prime of x, because the derivative f prime of a is limit x approaches a, f of x minus f of a over x minus a. So if you say what's f prime of x, then this becomes x approaches x and f of x minus x, f of x over x minus x, and it really doesn't work. So I would stick to the h is 0, but you can use this one, but you just need to realize you're fine. If I ask you to find f prime of x, you need to do this formula, and your answer is going to have a's in it, and you have to replace your a's with x's. So if you go through all this and you get the end a squared minus a, then your answer to the question would be x squared minus x. Hmm? Say again? You just replace the a's with x's. Yeah. If you use that formula. Okay, yes. Let me bring it up real quick. It's 23. It may not be. Okay, so this was number 23 on the review. It was implicit differentiation, and then you replace x and y. So you followed that. Everything was okay. Everything's good. Here's your slope. You go to the equation here. Negative 9/4 goes in. You distribute through. Then here I subtracted 2. Yeah, it should be 1/4. I don't know why I put 1/8. That's 1/4. Everyone? That should be 1/4. I won't fix it and send it back out. Y'all just figure that out. Any other issues? For number 13 on the review? Oh, you haven't looked at the answers yet, have you? 13 was kind of supposed to be, yeah. So look, number 13 is a good example of how time can be wasted on the test. On 13, you're asked to find the derivative of this using, and then so you look at it and you're thinking quotient rule right off the bat, right? So you do quotient rule, you go through all this, and then you start to do all the algebraic simplification. And if you get it all right and simplified, you get 1 as an answer. However, if you would have started the problem before you did anything, before you take a derivative, and you would have factored an x out, then the top and bottom cancel, and y is x. And the derivative of x is 1. Ha! This was right out of the book. I didn't look. This problem, when I got it, I grabbed it out of a book. Okay, I just took it out of a book, and I did the problem. And then after I got 1, I said, wait a minute. The only way you can get derivative of 1, or the derivative to be 1, is if it was x to start with. So I went back, so I thought I had made a mistake, so I went back and I looked, and I said, wait a minute, what's the original problem? I said, oh, crap, if I would have factored an x out, I would have been there. So it was a ha on me, too, you know? You have to pay attention to this thing. You know, I'm not going to intentionally do that to you. I want to see the quotient rule. This, to me, wouldn't test you on anything, because if you saw it, it canceled, it's over. Derivative of x is 1, so. This. Right here? Something like that? This one right here? On a problem like this where it's all polynomials, where things can be distributed pretty clean like this, I would expect you to get to at least this right here. Oops. This right here. You know, if you don't realize that the top factors and all, okay, that's fine. But On the test, I don't think it's going to factor and cancel. No? The one that, with what I just said? Okay, let me go back to it. All right. Okay, what do you want me to go through? This right here? Are you asking me or are you asking each other?
I think they're asking each other.
Okay. Then what I recommend we do is we just talk about that at the end, like afterward. All right? Any others? 20 on the review? Yes? Okay, this is a good problem. I never gave you something like this. That is why it's a good problem, because it requires you to think a little bit about what's going on. Let me see. Where's the actual review here? Let me bring up the question. Okay, here was the question in case you haven't seen it. Find where the tangent line to this curve is parallel to this line. Hey, y'all can figure that out. Keep it down, please. We can't stop class for one problem. I've gone through it already, so. Okay, so look. I'll give you I need a new sheet, so. I'm going to just draw on the board. Screw it. Look, we have a curve, right? We have some curve, and then we have a line that's been given to you. Okay, the line was x minus 2y equals 1. Here it is. We have a curve. The curve was, what, square root of 3 plus x squared? Here's that curve. I want to know where on this curve the slope of the tangent line is parallel to this line. Where is that slope parallel to this slope? Make sense visually? So that means I need to know the slope of that green line. So I need to know the slope of that line. How do you find the slope of a line? Well, you can put it into the form y equals mx plus b, which means you can solve this equation for y. If I solve this equation for y, right, I move this to this side, move the 1 back over. Here's where I am. I divide both sides by 2. I get this. This looks like y equals mx plus b. So I know the slope of the line that I'm looking at over there has a slope of 1/2. So basically what I need to know then is when does the derivative of my function equal that slope? So when does my y prime equal 1/2? Does that make sense? Yes? When does my derivative equal 1/2? So I have to first find the derivative. So the derivative was a chain rule. So you do derivative square root of something is 1 over 2 times the root of what's there. Then times the derivative of what's inside, which is 2x. And then you cancel the 2's, and there's your derivative. So the question now is, when is that derivative equal to 1/2? So I set it equal to 1/2. Any questions up to this point? Sure. Set the derivative equal to 1/2. What did I do in the next step? I did like a cross multiplying. I multiplied both sides by the square root. I multiplied both sides by 2, and this is where we get. That's a radical equation. To solve a radical equation, You isolate the radical, which it is by itself on one side of the equation. I square both sides of the equation. That's this step, right? The root goes away on the right side. On the left side, I squared it, so the 2 becomes a 4, the x becomes x squared. And now I notice I have an equation with quadratic, right? X squared. So I move all my x's to one side. Or sorry, no. I actually isolated the x's on one side. I left the numbers on the other. I only did it that way because I could see that the 3's were going to cancel and I get 1. In general, if it was a quadratic equation, I just would have brought everything to one side, used quadratic formula or something like that, factored, AC method. But in this case, it was a pretty clean quadratic. Do y'all see that? X squared, divide both sides by 3, x squared equals 1. Take the square root on both sides. You get plus or minus 1 on for x. And then I had to check those 2 answers. Why did I check those 2 answers? Well, because anytime you have an equation, which we had, right? This was an equation, and we chose to come in there and square both sides, right? We did that. Anytime you do that, you always have to check your answers, because there's a possibility that you introduce what's called an extraneous solution. So that's what I've done. I have to go back and make sure that those answers work. When I try and plug 1 in to the original equation, which is this equation, right, the one I'm trying to solve, when I plug 1 in for x, it works. But when I plug -1 in, it does not work. So I chunked the -1, and that means x equals 1 is the only possible answer. So if I go back to this curve, and I go to x value of, I can tell you right now, if I go to x equals 1 right here, that slope of that tangent line is the same as the slope of this line. What if I had said, find out where the slope of the tangent line is horizontal? That was on here, wasn't it? What does that mean? Set it equal to 0, right? Because slope of tangent line horizontal means that derivative is 0. This is the same sort of problem, except instead of setting it equal to 0, you're setting it equal to 1/2. It's the same sort of thing. Horizontal means 0. That's no problem. In this one, I'm not saying when is it horizontal. I'm saying when is it parallel to this other line. So when is it whatever that slope is, which in this case was 1/2. Hope that makes sense. Yes. Because I took the line that was given in the problem, and I set it equal to y. I solved for y, so that it looked like y equals mx plus b, which is the equation of all lines. Right? All lines that are written in this form, the m, the number in front of x, here is your slope. Does that answer the question? Yeah? Okay. 5 and 6. I can try. I've been through this with. This is one of those things that the people I've tried to help with this, it's like a light bulb. It just either it's like, oh, I see it finally, I see it, or it's just confusion the whole time. How many of you are the confusion the whole time for this? First, you got it. I know we worked on it and it finally clicked. Okay. So let's start with this one. I do intend to talk about new stuff today, but I'm worried about how much you'll actually retain. None of it. Okay, if that's our original function, and I want to sketch its derivative, I made that a little too big. Let me just. What did I let you have last time? The formula sheets and then a sheet, right? You can have that, all the answers, yeah. Same thing as last time. You can have a sheet with steps and procedures, just no worked out problems, along with the formula sheets. All right, so all we're trying to do is graphically represent the derivative of this function. So I always say try and go to your function and see if there's anywhere where you have a horizontal tangent, a tangent line that's 0, which would be like at the top of a peak or at the bottom. But in this particular problem, we don't. Why don't we have a tangent line up here at this corner? Because it's a corner, right? You can't have a derivative at a corner. The derivative is undefined. So I don't have that. But what I can say is that if I were to pick a point, like this particular x value, right? If I pick that x value and go down to my graph, and I ask you right there at that point, what's the slope of the tangent line? What does it look like it is? 1, right? So that means on my new graph, for my derivative, I'm going to go to the same x value, which is over here somewhere. I'm going to go and plot a point 1 unit high, because it's 1 there, right? And let me pick another point. So I go on the x-axis, go like here, come down, pick a point right there. What's the slope of the tangent line there? It's 1 again. So go the same distance over here on the x-axis and plot 1 again, which will be here. And then let's pick another point, maybe over here on the x-axis. Come down to this. What's the slope there? It's 1. So on the x-axis here, I go and plot a point up 1. Do y'all see that? In fact, if I pick any x value to the left of the y-axis, and I go to any point over there, what's the slope? 1. So that means if I were to plot all those points, it would look like this. Wouldn't it? Straight line. That's supposed to be straight. Until I get to where? Okay, what's happening at 0? Jesus. It's a disaster right here. Okay, so at 0, right, we said that the derivative was undefined because there's a corner. So what I'm going to do is I'm going to put an open circle there. Right? Now, what if I go to the right and I pick a point, I come down here and I say, what's the slope of the tangent line there? That looks like about -1. So instead of going up, I'm going to go down 1. I just keep doing that. Just another x value, come down, pick that point, it's -1 again. Anywhere to the right of the y-axis, the slope of the tangent line should be -1. So it's going to look like this. And then at 0, remember it's an open circle. So this is what your derivative looks like. Your derivative is actually a step function. Look at what you're saying. As you're moving along this graph up here, what's happening? Your slope is 1, 1, 1, 1, 1, 1, 1, then all of a sudden, and it goes to -1, right? It jumps over that little place. There's no definition of what happens there. It just kind of jumps from 1 to -1 instantaneously. Does that help a little bit? What's that? 6 is a little more involved, but you have to understand that one before we can do 6. So for 6, now what I'm going to do is I'm going to go and say, all right, I draw a graph right below it. Yes. Derivative doesn't exist. Nope. It's a great question, but it's not possible because the thing is, no matter how much you zoom in, right at 0, okay, right at 0, it has a value. To the left of that point, it's below. To the right, it's below. So to the left, the slope is this, and to the right, it's this. And remember that the derivative is a limit. And so remember on the limit, you have to come in from both sides. So as you come in from one side, it's doing this, and the other side's doing this. And so they're different numbers, 1 and -1. So no matter how much you zoom in, it's not going to be, the derivative won't exist. Which you've opened up a bigger question. When mathematicians were studying functions, they asked themselves a question. They said, look, is it possible to have a continuous function, okay, so a function you can draw without picking up your pencil, that is nowhere differentiable? Meaning, like the one we just did is a continuous function. I can draw it without picking up my pencil, right? There is one point where the derivative doesn't exist, right? Everywhere else, the derivative is fine. The derivative is defined. So the question was, is there a function out there that I can draw without picking up my pencil, but the derivative doesn't exist anywhere on it. And so it was studied. It was a very, very challenging question. It was not known, and finally it was discovered by a guy named Weierstrass, and he came up with the Weierstrass function. And what it is, I'm talking about is because you kind of hit on it. It's a function you can draw without picking up your pencil, and it looks like this. It's a bunch of corners like this. But if you look in between these two corners, right, that looks like it's differentiable, doesn't it? Because you can draw it without because there's no corner in between here. But if you zoom in on this function, and you zoom in just on that, that looks like this. A bunch of like saw blade teeth, And so there's a bunch of places in here it's not defined. And then when you zoom in on each one of those little jagged edges, it's more jagged edges. And when you zoom in again, it's more jagged edges. And you keep zooming and zooming, it's always jagged. So it's like an infinitely vibrating pen where you're always having corners at every moment in time. The function is well defined and it exists. It's differentiable nowhere. And if you look it up online, it's a weird looking function. It has infinite summations and cosines and stuff in it, but it's pretty cool. Sorry. All right, so back to this. If I'm trying to graph the derivative, first thing I would look at is where's the derivative 0? Because in the last problem that didn't help us, right? Because we didn't have any peaks and we had corners. But here it's kind of obvious, I think, that here our derivative would be 0 and here, right? So I'm going to say, what's the corresponding x value? Well, I don't know, somewhere around here on the x-axis, right? Somewhere around there, my derivative would be what? 0. So I put a dot on the x-axis. That's y equals 0. And then I'm going to have another one right around here, right there. Is that part of it okay? Okay, if I pick a point, let's say I pick this point, x value about right here. What's my derivative, positive or negative? It's positive, right? Positive 1, positive 2. You can't really tell, right? But it's positive. As I get closer to that red dot, my derivative is still positive. Slope of tangent line is still positive, but it's starting to flatten out. So it's starting to come to 0, isn't it? So to the left of this red dot, which means to the left of this red dot, my derivative should be positive, but getting closer to 0. So it's got to look like this. These are positive numbers, but they're getting closer to 0. Then once I get past the top there, I start coming down this side. What's my derivative? The whole time I'm coming this way. It's negative, negative, right? And then eventually it has to go back to what? 0. So on my derivative, I've got to be negative values, but eventually I have to come back to 0, which is what I just did. Once I go past the dot, my derivatives are what? Positive, and they stay positive the rest of the way, don't they? So it goes like this. I hope that helps. Did that help? You pick as many as you need. I don't want to say 2 or 3 or 8. It's just as many as you need to understand the graph, to understand the graph of what the derivative is doing. All right, what else? How about number 11? Anyone have trouble with 11? I can do what? So here's what 11 was saying, just so you know. It says the position of a particle is given by s of t equals negative t cubed plus 6t squared plus 1. This says s is in feet and t is in seconds. Sorry, I know that's kind of hard to understand what the hell I was talking about there. But your measurement of the position is in feet, and the measurement of time in this problem is in seconds. So it says find when the velocity is 0. So how is the velocity related to its position? It's the derivative. So this first question is asking, when is the derivative 0, right? Set the derivative equal to 0. So that's the first thing that is done here. I take the derivative, right? This is first thing what I'm going to do. The velocity needs to be 0, which means the derivative of the function has to be equal to 0, which means here is the derivative, which I just applied power rule to this, right? You don't have to do limit definition. Please do not do limit definition the whole test. You won't have time, right? So derivative here, and then now I have to set that to 0. It's a quadratic. I choose to factor it. You get two solutions, 0 and 4. There are two places when this object's velocity is 0. They are at t equals 0 seconds, and then t equals 4 seconds. Now, in part 2 of this, pardon me? Yes. As an answer? Yes. Because the function is defined there. So when this object starts moving at time equals 0, the velocity is 0. So that makes sense that for this particular object, when we started the clock, it wasn't moving. It was stationary. And then later on it moved, and then at 4 seconds later, it stopped. Its velocity was 0. With me? Okay. All right, now this second question is a little tricky. Find the acceleration when the velocity was 0. That doesn't say set the acceleration equal to 0. It's not saying when is the acceleration 0. It's saying what is the acceleration when the velocity was 0. So you have to have gotten part 1 right to get part 2 right. Because this wants you to take the 2 points in time when velocity was 0, right? I want to know what the acceleration is exactly at those 2 points in time, at t equals 0 and t equals 4. So I have to find the derivative, find the acceleration, which is the derivative of velocity, or the second derivative of the first function. So I take the derivative of that quadratic up there, I get this. And now I just plug 0 into it, I get 12. And I plug 4 into it, I get negative 12. And the measurement of acceleration, is units per second. So feet per second squared or in feet per second squared. Does that make a little more sense now I've been through it, or no?
On the second one, when you plug in 4, how does it -12?
I plug 4 in right here. 6 times, it's negative 6 times 4, yeah. All right.
I thought that, remember one thing you were talking about the second derivative acceleration, so I did that.
So you just took the first and second derivative but didn't do anything with them? Okay, now you see that in the wording of the problem you're having to do a little bit more with it? Okay. That's correct. For part 2, you would need both. And then for part 1, you would need both. Yeah. So this is the problem you're talking about, right? Yeah, this problem kind of sucks. It's square root of a quotient. So you have chain rule with quotient rule. That's what I put up here to kind of help guide you through this. So the first thing I did is I didn't do a derivative. I just rewrote the square root as to the 1/2. That's just my choice. And you could have left it, but whenever you feel necessary. I only did it because I was hoping it would help you. You could have done 1/2 root. Yeah, I was afraid it might confuse you if I did it as a root. So, but I also told you should be able to go use either way. You know, like be comfortable using the square root or going to the 1/2. So I first switch it to 1/2. Now the derivative. We have a function, which is a quotient, sitting inside of a bigger function, which is a square root. So chain rule says start from the outside, work your way in. Derivative of something to the 1/2 is 1/2. That's something to the negative 1/2. Times, now the derivative, what's inside. But that's a quotient rule. So I have to do derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. There it is. And then I multiplied through the 2t right here, multiplied negative 2t through here. Cleaned this all up, it turns out to be negative 6t on top there. This bottom turns out to be this. Now, what the hell happened here? Is that what you're wondering? You tell me, what happened from here to here? That's right. I noticed my negative exponent turned into a positive exponent, but my fraction flipped. That's a property of exponents. Property of exponents says x over y to the negative n equals y over x to the positive n. That if you ever have a fraction to a negative power, you can flip the fraction and make it a positive power. So that's what I did there. So I flipped those. That's this. Now, what did I do? Here to here? Yeah, I just applied the power to each one, the top and bottom separately. So that's this. Why am I doing this? Because I realized that these two right here have the same base. And so I was trying to get the power on this one, the power on this one separate, right? That's why I wanted to pull it out from here, so I could see the cancellation that I'm going to get there. So what's 1/2 take away 2? Negative 3/2. Negative 3/2. So this right here becomes t squared plus 1 to the negative 3/2 on top, right? I drop it to the bottom, it becomes a positive 3/2. What does it mean to raise something to the positive 3/2? It means the square root of it cubed. So this is that piece right there. This and this, that's it right there. And then, since this is cubed and it's a square root, I can pull one of them out, and that's this. Look, when I was a Calculus 1 student, my algebra was not like this. Like, I didn't see all this, okay? The only way I saw it is by looking at the answer and trying to get my algebra to work to that answer. And that's how I got good at algebra. Calculus forces you to get good at algebra. I mean, you just have to. If you want to be able to simplify things, all these little rules, right? You just keep having to apply them. Can I do what? This one and this one? Like where this comes from this? I'm doing, what is something to the 1/2 over something to the 2? What is x to the 1/2 over x to the 2? X to the negative 3/2. That's on the top. But then I drop it to the bottom, which makes it 1 over x to the 3/2. But that means 1 over the square root of x cubed. This is all properties of exponents right here. So all this is property of exponents. Drop it down. What does that mean? It means this. But instead of x here, I have what? T squared plus 1. So that's where this comes from. Did that address your question in some fashion? This right here? Oh, that's just from here. That's just what this means, right? Yeah, nothing happened with that. This right here means t squared plus 1 times t squared plus 1 times t squared plus 1, right? That's what that means, cubed. Every time you see a group of 2 in here, it can come out as one of them, right? Like if I had x squared under square root, it would just be x. Same thing. So that's this right here. Here? Here? Of the whole thing? It's okay. Yeah. I mean, it's right. It's just a question of how far does it need to be simplified. Look, there is a real like conflict within the math department as to how much simplification needs to occur. There are some faculty members here that if you take Cal 1 with them, if you don't get to this, it's wrong. Okay? It's wrong. I'm a little more lenient, okay? I want to see the proper use of the derivative. I want to see the proper rules applied. I want to see some skills as far as algebraic manipulation is concerned. This right here is not enough, okay? This is not enough. You've got to be able to go further than that. Seeing all these little details, I don't know, maybe you know, you don't see them, but I'm not going to penalize you too much for that. But you got to be willing to take on the algebra of this course. You have to confront it, have to figure out where your weaknesses are, work on them, and work on the algebra. I can't look. Let's not look at where, because everyone wants to know where to stop. You stop when your algebra runs out. When you don't know what to do anymore and you don't know what else canceled, that's when you stop. I'm not going to hold myself to any, well, if you take it to this step exactly, then I will only take off this. Look, I'm going to look at it. I'm going to know if your algebra is good or bad. I'm going to know it when I grade it. I mean, it's very easy to tell whose algebra is good and whose algebra needs work. Very simple. So just follow your own, rules as much as you can. Do the best you can. I will give you partial credit. Just show me as much partial work as you can. All right. Someone asked about number 1. This has somehow turned into a review day. What is the question on number 1? What about it? Yes. Okay. All right, hold on. Let me get here. Okay, so here. Find the equation of the line tangent to, okay, I need the equation of a line, right? I need the equation of a line. It needs to be tangent to some curve. So I need to be able to use that formula y minus y1 equals m times x minus x1. Remember that formula? Which means I need a point on the line, which I have, right? I have a point on the line. I just need the slope. And where's the slope going to come from? Where's the slope of that line going to come from? Well, it has to be tangent to this curve, right? So it's got to be the derivative of this function at this particular point. So I need to find the derivative of this function. But my instructor is being kind of an you-know-what, and he's making me use the limit definition to find the derivative. I wish not, because the derivative, that's 5 minus 2x, right? That's a derivative, 5 minus 2x. And then I could just plug 1 into that, and I'd have my answer, 3. But he wants to see the limit definition. So that means I have to, using the limit definition, the slope of the tangent line at x equals 1, where does x equals 1 come from? I gave you the point, right? 1, 4. So the x-coordinate was 1. So I used that definition, the good old definition, limit h approaches 0 of f of a plus h minus f of a all over h, replacing a with 1. There's the definition right here, replacing a with 1, and then just plug it all in, do all the work, and you get 3. Once you know the slope of the tangent line, you come here and you get the equation. There's the equation. Y1, x1 is in here, m is right there. That's 3. Did I address your question or not? Who asked me about that?
I did. I'm getting confused in the very first one reading the 1 plus
Where, right here? This? I'm plugging 1 plus h into the function. What was the function? 5x minus x squared, right? If I say go replace all of the x's with 1 plus h's, right? It becomes 5 times 1 plus h minus 1 plus h squared. Oh. You understand where it comes from now? Yes. Yeah, absolutely. Then plug in 1. Plug in the x value, right? The derivative, you just did this using the power rule, would be this. That's the derivative. Now, at x equals 1, plug 1 in here, 5 minus 2 is 3. It would have matched up. So you can always check your answer that way. Well, okay. Well, let's talk about some new stuff then. My intention is to put a problem from today's lecture on the test as a bonus, okay? To make it worth it for some of you, you know, that want to have today somewhat pay off a little bit. Thank you. We will do more of today's stuff when we come back, all right, after the test. But we need to at least start it today because we can't waste too much more time. All right, so this is related rates 2.7, I believe. Yeah. I'm hoping you read the notes, but there's a pretty good chance that you may not have had time. So I'm just going to show you one picture here, which I think kind of summarizes what's happening. If I give you a circle, okay? If I give you a circle, and I tell you the radius, can you tell me what the area is? Yes? Area is pi r squared. Agreed? So if someone just fixes a value, you know, radius is 2, you can tell me the area. Or if I tell you that, hey, look, there's a circle out there that has a certain area, let's say 40 square feet or something. Once you know the area, you could actually go back and get the radius, couldn't you? So if you fix radius, I can find area. You fix area, I can solve for radius. And that would be pretty we'll say pretty trivial, right? Just solving for one variable in an equation. However, in calculus, everything in calculus that we do is about what's happening as things are moving, right? As things are changing. How does one variable change with respect to the other? dy dx meant the instant rate in change in y with respect to x. So as one thing changes, like the radius changes, how does the area change? So what I want you to pay attention to very closely in this picture here is I have programmed the computer to make the radius change at a fixed rate. So the radius is going to grow 1 unit every second. Okay? So every second it's going to grow 1 unit. And it's going to be moving. Now, it may not be exactly 1 second, all right? But, okay, there the radius is 1. Here the radius is 2, 3, right? 4. Y'all see the radius? 5, 6. So every second, or every whatever it is, it's growing at a constant rate. Y'all follow? Okay. But the area, as we grow, the area is changing also. If the radius is changing by 1 every second, is the area changing by, let's say, 1 every second? Is it linear also? Take a look at the area here. Okay, I want you to count. Look at the area right now is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. See how it's getting faster? Do y'all see how the area is getting faster and faster? Let me slow this thing down. Start over. Okay, look at the area. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. See how I'm counting faster? So in the beginning, the area was coming up kind of slow. Now I can't count. Look at that. 39, 4, 4. See, I can't even count anymore. So even though the radius is going up nice and steady, 1, 2, 3, 4, the area is like slow, and then all of a sudden, the area is getting bigger faster. Make sense? So the question becomes, at a specific instant in time, like let's say right there, how fast was the area increasing? Not what's the area, because if I stop time, everyone can tell me what the area is. But it's at an instant, how fast was it growing? Make sense? So that's what we're going to start today with. I'm going to give you a problem where I have a circle, the radius is growing at a constant rate, and I'd like to know at a certain point in time how fast the area is increasing. So how do we do something like that? Calculus, we're going to need it, right? So first example, a circle is growing so that the radius increases at a constant rate of 2 feet per minute. Let's go per minute instead of second. So you've got this circle. It's growing. Every minute, the radius increases by 2 feet. Every minute. So it's a slow growing circle, right? But it's a constant rate. So it's always, now the area is changing, but we already saw from the picture, the bigger this thing gets, the faster the area grows, right? A little bit of a change in area, if the circle's huge, a little bit of change in radius makes a big change in area. All right, so the instructions for this section, if you did read through them, say to do this, you have to find some sort of systematic approach to it. And I always recommend that you draw 2 pictures. Okay, the first picture that you'll have, I like to separate my pictures with a line. I have the instant, oh, hold on, I forgot something in the problem. A circle is growing so that the radius is increasing at a constant rate 2 feet per minute. Find the rate the area is increasing when the radius is 4 feet. That's the whole problem. Sorry, I forgot to write the rest of it down. Am I asking you what the area of this thing is when the radius is 4 feet? No. I'm saying at the instant the radius gets to 4 feet, at that instant in time, how rapidly is the area increasing? Now, you may be asking yourself, like, why in the world would you ever need to know the rate at which the area of a circle is increasing, right, at a certain moment in time? I mean, these are good questions. Right now, we're just trying to start with a very simple geometric problem. Very simple. But you can have things like, I mean, the first thing that came to mind is if you've ever seen like a piston in an engine, you know, the piston goes up and down through the cylinder. The piston is attached to a crankshaft that does something like this, right? Well, you might want to know at a specific instant in time the speed at which the piston is coming up the cylinder. Because this is like a circular motion, and so the speed that this point travels is somehow connected to how fast this is rotating and how long this arm is and everything, right? It's all interconnected. So how does the change in rotation here affect the speed of the piston here? Well, you're trying to find a relation between the rates of things, between these variables, related rates. Right now we start out very simple. How is an area related to its radius? Later on, the problems become more advanced. And you can any time you can connect two things together through an equation, you can always find the related rate between them. So it's useful later. Don't be thinking of it as, geez, man, I'm never going to look at a circle and care how fast it's growing. All right, so here are my two pictures. I have what I call my instant and then my general picture. I recommend you draw two pictures. One that talks about what's happening at the instant in question. So the thing is growing, and then take a snapshot right at that instant. What does it look like? Compare that to what it looks like if you're not snapping a picture and you're allowing everything to change. So at the particular point in time, I have a circle, don't I? Yes? Okay. So what can you tell me about that circle at the instant in time? The radius is 4 feet. Everyone agree? Okay, so I'm going to say this is 4. We can put feet. We don't have to. Do you know the area of it? You could, right? Now, normally I wouldn't write this down, but because it's our first problem, I'm going to say, look, we want to know about the area, don't we? We want to know about how fast the area is changing. I actually know the area right now is pi times 4 squared, right? So I actually know right now that the area at the instant in time is 16 pi. That may or may not become useful later, but that's what I can tell you about a circle with radius 4. Could you tell me what the diameter of it is? Sure, right? Double the radius, it's 8. But we may not need that. I'm just trying to think of all the things we know about this so far. Do we know its circumference? What's the circumference of a circle? 2 pi r. So I could actually tell you right now that the circumference of this is 8 pi. Now, do I need that? I don't think so, because the problem mentions nothing about circumference, does it? All right, so what's the general picture then? So now imagine that you're not snapped at 4 feet. So what variable is changing in the problem? What thing is changing? The radius, right? So when I label this picture over here, and my radius, I'm not going to call it 4, I'm just going to call it r. That's my radius. Do y'all see the difference between my general picture and my snapshot instant in time picture? Once you establish these two pictures and you've written everything down, like I know area here is not 16 pi, it's what? Pi r squared. That I can't fix my r, so I'm just going to leave it. The next thing you want to do after you've drawn your pictures, and it's not really in that order. Sometimes you draw the picture and then you go to the next step, or you do a combination of the two and look back and forth. But at the end, we want to have pictures and then a list of what was given in the problem and what it is we want to find. All right? What was given and what we want to find. So let me list out underneath this different color. I'm going to say what was given to us in the problem and what we want. Okay, let me list out what we're given and what we want. We are given some numbers in this problem, aren't we? And they have some very, very special meanings. I have a circle growing so that the radius is increasing at a constant rate of 2 feet per minute. Isn't feet per minute a speed? Like a velocity? And wasn't the velocity always the derivative of a position function? So whenever we see rates like this, feet per second, feet per minute, miles per hour, whenever we see that in our word problem, we need to identify that this is actually a derivative. It's the value of a derivative. In this particular case, it's the speed of what? the radius, right? Imagine that the radius is just a little point that's moving, right? That thing is moving at a rate of 2 feet per minute. So the way I'm going to write that, I need to somehow tell you it's a derivative, is I'm going to write that what I'm given is that the derivative of r, okay, derivative of r, with respect to t. Now, t here is time. Time here in this problem is measured in minutes. So think about what this is saying. The speed at which the radius is changing with respect to time is given to me to be 2 feet per minute. Does everyone see the radius here, r, divided by time, is almost like the feet divided by minute? Feet is the measurement of our radius. The minute is the measurement of time. Y'all with me? So I'm given that. What else am I given? I know what the radius is at the instant that they're talking about. So I am given that, right? What do you want? Let me ask you that. What is it that you want? What are you trying to find? The rate. So as soon as you see the word rate, you're thinking derivative, okay? I want the rate of the area. So I want to know how fast the area is changing. So anytime we talk about rate, I'm going to use a derivative. So I want to know the derivative of area A with respect to what? Time, again, right? How fast is the area changing with respect to time? This is the notation we're going to use for these problems. I'm given the rate that the radius is changing with respect to time. I want to know the rate which the area is changing with respect to time. So I'm going to put a little equals, question mark, I don't know. Okay, I want that, but I don't just want it at any point in time. I want that at exactly a specific moment, don't I? So next to this, I'm going to put at what point in time? When what's 4 feet? So at r equals 4. Or you could say when r equals 4. Let's just take a step back. Big picture here. You have exactly the moment in time. You've got a general picture of what the circle looks like. You've written down what it is you're given. You're given the rate at which the radius is moving. You're written down what you want to find, the radius, the rate at which the area is changing at a specific point in time. Any questions on that? No? Okay, now we're ready to do the calculus. The calculus part of this problem comes in when you look at your dr up here and your dA, okay? What you're given and what you want, right? I'm given information in terms of the radius. I know how fast it's moving, and I know that instant in time, don't I? I want to know something about the area. So at this point, it is up to you, as the person trying to solve the problem, to come up with any equation you can, anything that exists out there that you know of, that connects the area of a circle to its radius. Area is pi r squared, right? Any equation you can come up with. Would circumference equals pi r work, or 2 pi r? No, because it doesn't have area in it. You see what I'm saying? Like you need something that connects the area to the radius, which we just happen to have jotted down, didn't we? So this next step in this process is to find your equation. So the equation that I have is area equals pi r squared. So far we've done really no calculus, other than maybe we've used some calculus notation, haven't we? Other than that, we haven't done any derivatives or anything. So if you have a circle, here's the relationship between area and radius. I can always differentiate an equation implicitly. Right? If I had an equation, that was the last section we covered, we could do the derivative on both sides. Yes? So I came in here with this squiggly line like this. I said take the derivative. In our homework in the previous section, we were always doing y prime, right? And we said that that was really dy dx. But I said, be careful. We want to be able to use the notation dy dx because we always have to know what we're differentiating with respect to. Why was it that when we were doing dy dx, why was it that when we were trying to do this, when we got to x, the derivative of x was 1? Why? Because the dx on the bottom, right? That said, what's your variable? X. So when we said, what's the derivative of x with respect to x? We said 1. But what happened when we got to y? We said, what's the derivative of y with respect to x? We'd say it's y prime or dy dx, right? We couldn't turn it into a 1. That is critical because now when we take the derivative of this, what are we going to do the derivative with respect to? Time. Why? Because that's what I want, right? I want to know the rate at which the area is changing with respect to time. So the thing I'm differentiating with respect to is t. Does t appear in here? So we will never take a derivative and get 1. Every time we have a variable and we take its derivative, it'll be whatever the derivative of that is with respect to time. It'll be like the dy dx was. It won't go away. It won't turn into 1. Let's see if this makes sense. Okay, derivative of area, left side. What is the derivative of area with respect to time? So what is the derivative of A? dA dt. It's dA dt. That's what it is. Equals, now on the right side, pi is a constant, right? So that I don't have to worry about. We already know constants. That's never going to change in this class. Constants will always behave the same way. So I'm just going to cover up pi. I'm going to bring it down here. What's the derivative of r squared? Okay, hold on. 2r. Are you done? No, that's the power rule on r squared. The 2 came down. The 1 is up here. But now you have to go inside and take derivative of r. What's the derivative of r? dr dt. Do you follow that? Any questions? We're done. And we're not done with the problem, but we're done. That's the calculus part of the problem. The calculus is over. Just taking that derivative. Now look at what we have in this new equation. dA dt. Isn't that what we want to know? Okay. Pi times 2. R. Now we can actually let R be 4. We can fix the moment in time now. If R is 4, right, we got that. What's dr dt? It's 2. So now it's just plugging in values. Just plug everything in, and we can find what dA dt is. So bringing this up here, now let everything be the instant in time. So dA dt equals pi times 2 times 4 times 2, which is 16 pi. Great question. I was just going to ask you the same question. So this is our change in area with respect to time. And I don't know if you've noticed, I didn't write any of the units here. Like I could have put 4, what? It was 4 feet, right? And then 2, wasn't that 2 feet per minute, right? It was 2 feet. I didn't bother with the units. Now here's why I don't bother with the units. Because I think the units are actually hidden right in here. Time. What's time measured with in this problem? Minutes. So I know that I'm going to have per minute, right? The question is, what's the top? Well, it's the area, right? How do we measure area? Units squared, right? Feet in this question, right? It was feet, so just feet squared per minute.
But if we were to put in the units, we figured out that feet
would be feet squared. Yep, it'd be the same thing. I just think sometimes it gets a little tedious to carry the units along the whole way. At exactly the instant that the radius is 4 feet, the area at that instant would be increasing at 16 pi square feet per minute. It happened to be, coincidentally. Now, does everyone realize that just an instant later, at 4.001 feet, the radius being 4.001, that your rate of change, your DADT, will be different? This only applies at that instant in time. Also, something to point out. What would have happened had you got all gung-ho and you plugged in your 4 right here before you took the derivative? You would have had area equals what? 16 pi, and then you would have taken derivative both sides. You would have had dAdt equals what? Pi times 16? That's a constant, right? What's the derivative of a constant? 0. So you would have had dAdt equals 0. Why? Because when you plugged in 4, what did you do? You stopped the circle from growing, right? Look at it that way. It's kind of like if I'm running around, if I'm running across the room and I say right now, how fast am I going? Well, I'm not. I stopped, right? I'm not moving. I don't have a speed. Instead, it's what we're doing is we're just running and saying right then. When I said then, that's when I wanted to know. So what we did is we found an equation that tells you how the speed of the area is connected to the speed of the derivative without stopping anything from moving. Once you find that equation, then you come in and you can stop stuff. I don't know if that makes sense, but the order is so important. You can't freeze it in time until after you've taken the derivative. Yes. Yes. Uh-huh. Pi is a constant, so I bring it down. Right? You just bring the constant down in front. Derivative of r squared is 2r. It's one of the first rules that we learn. You can do product rule with a constant, but you don't. With constants in front of functions, they come along. 3x squared. Derivative of that is 6x, right? You leave the 3 alone. You bring the 2 out front, and it becomes 3 times 2 is 6. But the 3 just comes along with us. Derivative of 3 sine x is 3 cosine x. What happened to the 3? It just came along. Right? Product rule? Because it's not a function of x. This is not a function of x. It is a constant. You can do product rule. It's just a waste of time because you don't. It's more work than you need. Because when you take if you did product rule right here, what's the derivative of the first one? 0. So that's why even do that. And then the other one would be derivative of this, which would be cosine x times this one, which would be your 3. So you would do 3 cosine x again. I mean, it'd be the same thing. It's just overkill, and kind of even worse. It concerns me when people take something like this and do product rule. It concerns me that there's a breakdown in understanding of how to deal with the constants. You want to just bring them along the whole time if you can. Okay. This one right here. That was this right here. drdt was given to me in the problem to be 2. So all I did was replace, right? Pi, 2, what was radius? It was 4, and then this was 2. How about this one? This is the same sort of scenario, but this time it's 3-dimensional. It's a sphere instead. You have a sphere. It's growing, right? A ball. Look at the radius. The radius is coming up at a specific speed, right? Well, start this over. Let me count the radius. 1, 2, 3, 4. So the radius is constant, right? 5, 6. But look at the volume. It's just taken off, right? In the very beginning it was slow, but man, it just blows up. right? See how fast that volume is getting big? Look at 1, 2, 3, 4. Ah, it's all nuts, right? So definitely, if the radius grows a little bit, the volume grows a little bit. But then if you go a little bit bigger with the radius, the volume grows even more. And then, right? So this is just like the circle. The only difference is our geometry is different, right? It's not a circle, it's a sphere. So let's see if we can knock this one out. We'll be done for the day, all right? Let's say we have a sphere with a radius increasing at 5 meters per second. That's huge. That's a lot. That's really quick. That's 5 meters per second. I'll put second like that. Little m is going to be meters for us, all right? It's not that important, but sphere with radius increasing in 5 meters per second. Find the rate the volume is increasing when the radius, or you know what, when the diameter is 4 meters. A sphere, the radius is increasing at a certain rate. Find the rate at which the volume is increasing when the diameter is 4 meters. I'm going to draw 2 pictures. I'm going to have my instant in time. I'm going to have my general picture. How do you draw a sphere? I recommend you draw a circle, and then you do like this kind of elliptical, like almost like an ellipse in there, across the center. Kind of gives it some of that three-dimensional look to it. Then you draw the center of the sphere like that, and then your radius. What's our radius in the instant in time? Careful. It's 2, right? I gave you the diameter. The diameter is always twice the radius. So this is actually 2 meters. That's our radius. I'm even going to label it R. Anything else you want to tell me about a sphere? It's round. What? What's the volume? Do you know the volume of a sphere? Maybe not right off the bat, top of your head, right? But you also have formulas. In your formula sheet, reference page 1 actually has formulas for common geometric figures. Plus, there's also this thing, what is it? The internet, right? So there's never going to be a lack of information out there for you, right? You can Google sphere and it'll give you more than you need, right? So we get it. The volume formula is 4/3 pi r cubed. That's the volume formula. So I could actually tell you what the volume is right now. The volume would be 4/3 pi r, which in this case is 2 cubed. So the volume would be, what? 2 cubed, 8 times the 4 over there, 32/3 pi. That's the exact volume of that sphere at exactly that moment in time. Now let's draw a general picture. It's a pretty good sphere. Happy with that. What's my radius in this picture? It's r, because r is changing, isn't it? R is changing throughout this problem. Since r is just r, I know my volume over here would not be fixed, so it would be just 4/3 pi r cubed. What are some other things I need to be thinking about and writing down right now? What's given to me, right, and what it is I want. So let's write down what's given and what I want. What's given to me, most of these problems, somewhere in there, there's a derivative, right? In this particular problem, I give you the rate at which what's increasing, the radius. And in my drawings here, I have labeled my radius r, so my given derivative would be dr dt is what? It's 5 meters per second. That's my dr dt. What is it that I want to know in this problem? The rate at which the volume is changing. So I want dv dt. And I want that when? At exactly the moment the diameter is 4, right? But we need to be sure we understand diameter equals 4 for us doesn't help. We really need the radius. But diameter being 4 means radius is 2, all right? We want to be careful not to accidentally plug in 4 for the radius, because that's not what we're looking at. Questions? I think we've got pretty much everything covered here, don't you? We need the equation. What's our equation? Anything that relates the radius to the volume, which we've already written up there. It's volume is 4/3 pi r cubed. What are we going to do now? Take the derivative, right? We're not going to plug in 2, right? We don't plug in 2 right now, because that means you have fixed it, and the derivative of that will always be 0. It's like saying, hey, stop moving, and then say, I'm going to figure out how fast you're going. You know, we can't stop it. We have to let it keep moving. Now I come in, take derivative. What derivative are we doing? Like with respect to what? Time, right? So this left one will be dv dt is equal to, now the 4/3 pi is a constant. So I'm just going to, no, be careful, it's attached to a function, right? So it just comes along, 4/3 pi comes along. I got you. And then I take the derivative of r cubed. 3r squared times dr dt. If everything is done correctly, you should have what you're given and what you want in this final equation, which we do have, right? dv dt is what we wanted. dr dt is what we were given. And then we also have radius in here, but we're allowed to actually fix our radius now. So I will replace radius with 2. I will replace dr dt with 5. And that will let me solve for dv dt. So we're there. dv dt equals, what is it? 80 pi total? Oh yeah, I didn't see that 3 there canceled out. Right there. Those 3's canceled. Is that okay? I didn't show the work. Just plugging in 2 here gives you 4. 5 there, that's 20. Then multiply that times the 4. Yeah. All right, now units. Volume per time. Volume is measured in what types of units? Cubic units, right? So feet cubed. Wait, was it feet? No, it was meters. It was meters cubed per second. Time was measured in seconds. So at that particular instant in time, the volume is increasing at 80 pi cubic meters per second. Because it's volume, correct. Units? I would say not a huge deal. No. Are you afraid you're going to mess them up? Well, I don't recommend you try and keep them throughout here. Just think volume is cubic, area is squared, and then just like linear would be just feet. Just normal, just problems that we're going to be doing are things like you have an airplane flying over your head, right? And you're trying to measure the distance between you and the airplane, how fast the airplane's moving away from you. Or if this is an airplane flying overhead and you want to know how fast this angle is changing. Look at this angle right here. I'm on the ground looking at an airplane flying to me. The angle's changing pretty slow, and then it goes real fast, and then it starts to slow down, right? Slow, slow, slow. Watch how fast here. Right there, that right in the middle. It's kind of like if you watch a car drive by. You're like, watch it. It's like, right? And then right in here, it's very fast. And then as it goes away, it's, right? You like the Doppler effect there I was getting to, the sound? Right? So if let's say I'm like a radar station, I'm trying to shoot down a plane or something like that, right? Then I need to know the rate at which I have to turn in order to keep up with that, right? And so, I mean, that's what a lot of these things are doing when they're trying to shoot things down. These like anti-aircraft guns, they're doing all these calculus computations at every instant in time so it can keep keep up with it. But all that comes from, look, there's going to be some right triangle trigonometry in here and stuff, sine, cosine, tangent. The applications are pretty endless. I just picked like certain ones. Street light. This is a person. This is a street light. This is a person right here running away from the street light, right? Trying to get away. And then you have it's the person. Oh wait, wrong one. You have the person, and you have the person's shadow in front of them. And the question is, how fast is the shadow going away from the person? Oh, this is a classic. You start pouring beer into a funnel, right? And you pour it at a constant rate. And so what happens is initially, the beer comes up very fast, right? But then the volume's getting larger because the cone tapers out. So if I pour in at a constant rate, initially, look, the level came up really fast, but then it starts to slow down, right? So you might want to know, like, at exactly the point that it's, I don't know, right there, how fast is it coming up? You can think about, like, beer. Just think about beer, and it makes the problem so much better. Right, in the beginning, or you could look at it the other way around too. Like instead of the beer going in, the beer is going out. You could just reverse the direction. Now, if someone's chugging beer, and so initially, go down slow, and then towards the end, I like it this way better. That makes more sense. Huh? Yeah, there is. We haven't accounted for that. Let's. Right, so initially the rate at which it's going down is very slow, but then it starts to get faster. So we can think about like, lakes drying up, right? Something like that. We have a certain rate at which the volume is evaporating, and so we want to know like how long is it going to take? At a certain instant in time, how fast is it coming down? I mean, there's so many different things you can look at, but there's a lot of geometry in this problem. There's similar triangles, and so we'll see. It's not going to be on this test. Your bonus question on the test will be tied into either a circle or a sphere. There's only so much I can do, What do y'all think? Y'all going to be ready? Study that review. I put the solutions out there for a reason. Look through them. Try and make sense out of them. Yeah, y'all can come in. Last week I didn't because obviously all that stuff I was changing. I haven't even been to my desk today. because I had to take over that class. I'll be there tomorrow. Tomorrow from 9 till 11, and then from, what time do I get out? 1 to 3, I think it is. I teach from 11 to 1 tomorrow. I'll go to my office right now, and I will put my office hours up so you can get in for them. All right?